Hello, I am 3STEM. This is Mr. Liu delivering to you a new subject that we're going to be talking about. We're just getting started into sequences and series. And we're not in room 52. We're sheltered in place still. I hope you guys are doing okay. All right, let's go ahead and talk about this. We're talking about lessons that come from chapter 11 in your book. 11.1 and 11.2 is what we're going to be covering today. And we're covering sequences and series, and particularly arithmetic series today. So some of this was already taught to you in IM1, and you are expected to know these things. So these bullets right here, be able to use common notation for sequences. So this a sub 1, a sub 2, through a sub n. That should be familiar to you. You should be able to identify a common difference, which is commonly using D, and to be able to propagate the first n terms of any sequence. You should be able to write an explicit formula with the for the nth term of a sequence. So finding what a sub n is equal to. You should be able to write a recursive formula for the next term of a sequence when you're given what a sub n is. And then today we're going to be also covering some things to add on. You will learn about a series, about how a series, and be able to add the terms of a sequence to make that series. You'll learn about something called sigma notation, so you'll see that Greek letter sigma, and we're going to be using that Greek letter as a frame to show how to describe a series. You'll also learn about formulas and finding partial sums of series, and you'll use factorial notation and simplify terms in factorial notation. So let's start off with the definition of a sequence. An infinite sequence is a function whose domain is the set of all positive integers, and the function values then are denoted a sub 1, comma, a sub 2, a sub 3, and on and on and on to a sub n, and even beyond. Those are the terms of the sequence, and if the domain of the function consists of the first n positive integers only, then the sequence is referred to as a finite sequence. And sometimes it's acceptable to use the first term and label it as a sub 0. So here in example 1, we're finding terms of a sequence, which is something that we're wanting you to understand how to do. So let me show you how that's done in part A. So A says a sub n is equal to 3n minus 2. You should probably do this, create a table, and call this 1. Give yourself some room. 3, 4, and we're saying the first 4 terms. So there's 1, 2, 3, and 4 for our values of n. And then we're saying a sub n, and in this case right here, it's going to be 3 minus 2. That's equal to 1. So we know that one. The next one is going to be 3 times 2 is 6, minus 2 is 4. And then we've got 3 times 3 is 9, minus 2 is 7. And then we've got 3 times 4 is 12, minus 2 is 10. So we see that for A, we have 1, comma, 4, comma, 7, comma, 10. So that's how we do that for that one. For B, we've got a sub n is equal to 3 plus negative 1 raised to the nth power. And so, and what you're going to see here is that this is an oscillator, and you'll see why I call it an oscillator. If you understand what the word oscillate means, you'll see that this is oscillating. Okay, so n, 1, 2, 3, 4, a sub n is going to be this. 3 plus negative 1 to the 1 is just negative 1, so that's going to be equal to 2. And then the next one is going to be 3 plus negative 1 raised to the 2, that's positive 1, and so that ends up being 4. Well, watch what happens here. 3 plus negative 1 raised to the 3, well, that's negative 1, so this becomes 2. And finally, 3 plus negative 1 to the 4th power. It's even, so that makes that positive. So 3 plus 1 is 4. So if you see what's going on here, the answers are just simply going to be 2, 4, 2, 4, and on and on and on. So that's just the first 4 instances of it. And that's example 1. Example 2 says here's a sequence whose terms alternate in sign. Well, so each of the terms now are going to alternate in sign. And that's done simply by just taking negative 1 and raising it to the nth power and making that affect the whole sign of the solution. So let's just go ahead and do this one. This just says find the first 5 terms. So we have a sub n is equal to negative 1, and that raised to the nth power, and that whole thing over to n minus 1. And we're just going to do our numbers again. So here's n, and we're going to go 1, 2, 3, 4, and 5 because they want the first 5 terms. So here's a sub n, and we're going to say negative 1 raised to the 1 power over 2 times 1 minus 1. So that's just going to be negative 1 over positive 1. That's negative 1. And then for 2, we're just going to say 1 on top because we know that negative 1 squared is positive 1. And then we got 2 times 2 is 4, minus 1, that's 3. So this is going to end up being positive 1/3. And then number 3, we know that's going to make it negative on top. So we've got negative 1, and we've got 2 times 3 is 6. 6 minus 1 is 5. And so we have negative 1/5. Negative 1/5. For the 4th one, we know that's going to be positive on top. And then down below, we've got 2 times 4 is 8. 8 minus 1 is 7. So we've got positive 1/7. And then finally, for the 5th one, we've got negative 1 because 5 is odd. And then 2 times 5 is 10 minus 1 is 9. We have negative 1/9. Negative 1/9. So if I'm going to write the list then for this guy, it's going to look like this. Negative 1 is the first term. Positive 1/3. And then negative 1/5. And then positive 1/7, and then negative 1/9. So here, the terms are alternating with positive and negative signs. So for example 3, find the nth term of a sequence. And so this one's saying, write an expression for the apparent nth term of a sub n for each sequence. So let's take A and take some starters here. We can do this. 3 minus 1 is 2. 5 minus 3 is 2. 7 minus 5 is 2. So guess what? D, which is my common difference, is 2. Because notice between every term, we're just simply adding 2. We know that a sub 1 is equal to 1. And this is something that you should have learned in IM1. That since we know that information, then a sub n is equal to 1, which is a sub 1, plus 2, which is d, times n minus 1. Now, I am expecting you to know how to clean this up, and so we have to distribute that 2, so that becomes 2n minus 2, and we're adding 1 in front. 1 plus negative 2 is negative 1, so we'll just call this 2n minus 1, and that's my a sub n in simplified form. All right, for B, let's do it this way. This one has an oscillator, notice. There's an oscillator there. It goes positive, and then it goes negative, and then it goes positive, and then it goes negative. So right away, I know this, that there's going to be a negative 1, and let's see, probably to the n minus 1 power, because if n is 1, and I say n minus 1, that's going to be to the 0th power. Negative 1 to the 0th power is positive 1. And so that's why that 2 is positive, right? So for the second term, let's see if that still works. For when n is 2, 2 minus 1 is 1. Negative 1 to the 1 power is negative. That's why the second term, which is negative 5, is negative. Okay, so we've got that part. Now here's the other thing, is now we can just pay attention to the 2, the 5, the 10, and the 17 and see what we're doing here. Well, let's see. The difference between 2 and 5 is 3. The difference between 5 and 10, that's 5. The difference between 10 and 17 is 7. Well, hold on a second. If I look at differences again and go for second differences, I see 2 and I see 2. That makes this quadratic. I don't know if you knew that, but that makes this quadratic, and I think that I see it, that it's just simply going to be that 2 is 1 squared plus 1 is 2, 2 squared is 4 plus 1 is 5, 3 squared, etc., etc. So watch what we can do. We can just say n squared plus 1. And let's see if that works. So for the first term, when n is 1, 1 squared plus 1 is 2, and that times positive 1, yeah, that's 2. And then try it again. When n is 2, 2 squared plus 1, 2 squared is 4, plus 1 is 5, 5 times 2 minus 1 on the exponent for negative 1, that does make it negative, so we get negative 5. And let's just do the last one, when n is 4, okay? 4 squared is 16 plus 1, that's 17, so we get the 17 part. And then 4 minus 1 is 3. Negative 1 to the third power is negative, and so we got it. And so here it is. A sub n is equal to negative 1 to the n minus 1 power, and then that times n squared plus 1. And there's our answer for B. So it takes a little bit of hunting around, but we can get there. All right, let's take a look at example 4. Example 4 is a really cool sequence. It's called the Fibonacci sequence, and it's a recursive sequence, which means it really can only be propagated by going one sequence at a time. And it's defined this way. The Fibonacci sequence goes as follows. If we start off with n being 0 as our first term, so a sub 0 is 1, that has to be there by definition, and you'll see why. And then a sub 1 is equal to 1, and then all the succeeding terms are going to be of this form, where a sub k now is going to equal a sub k minus 2 plus a sub k minus 1, where k is greater than or equal to 2. Look at my sentence on the right there. It says exactly the same thing, only in English words. Each term of the Fibonacci sequence beyond a sub 1 is the sum of the two previous terms. So since the first two terms of the Fibonacci sequence are 1 and 1, then a sub 2 then is going to be 2. And so write the first 6 terms of the Fibonacci sequence. Well, we can start off with if n is 0, 1, 2, 3, 4, 5, and 6, then we could just go, okay, I know that a sub n for the first term is going to be 1. And I know that a sub 1 is 1. But a sub 2 is 1 plus 1, that's 2. Now, we have to go back to the previous 2 for each term. So for a sub 3 then, a sub 3 is going to be 2 plus 1, which is 3. And a sub 4 is going to be 2 plus 3, that's 5. And a sub 5 is going to be 5 plus 3, that's 8. And a sub 6 then is going to be 8 plus 5, which is 13. So if you look at the Fibonacci sequence, you'll see 1, 1, 2, 3, 5, 8, and 13. Okay? The next topic is called factorial notation. If n is a positive integer, then n factorial is defined as this, that n factorial is equal to 1 times 2 times 3 times 4, and on and on and on, just every successive integer, all the way to n minus 1 times n. And as a special case, we say that 0 factorial is defined as 0 factorial equals 1. In example 5, we're going to be finding the terms of a sequence involving factorials. So watch how this goes. We've got a sub n is equal to 2 to the n, and that divided by n factorial. And we're going to make our first one going to be n equals 0. So let's see what happens when n is equal to 0. I'll just do that one right up here. A to the 0, a sub 0 is equal to 2 raised to the 0 power, and that divided by 0 factorial. Well, we've defined 0 factorial as 1. We know that 2 to the 0 is also equal to 1, so this is just going to be a sub 0 then is equal to 1. Okay, let's try a sub 1. A sub 1 then says 2 raised to the 1 power over 1 factorial. Well, 1 factorial is pretty boring. It's just 1. And so we've got 2 to the 1 is 2. So 2 divided by 1 makes a sub 1 is equal to 2. And so there that is, a sub 1. A sub 2. 2 raised to the 2 over 2 times 1. I'm just counting down instead of counting up, but it ends up being the same thing since multiplication is commutative. 2 times 2 is 4. 4 divided by 2 is 2. So a sub 2, that's 2. Let's go for a sub 3. A sub 3 is going to be 2 to the 3rd power over 3 times 2 times 1. 2 to the 3 is 8. 8 over 3 times 2 is 6, times 1 is 6. So we've got 8 6, or there's a common 2 in the top and bottom, so we can call that 4 thirds for a sub 3, 4 thirds. And then a sub 4, 2 to the 4 divided by 4 times 3 times 2 times 1. So 2 to the 4, that's 16. That divided by 24, 16 over 24. They have a common factor of 8, so that becomes 2 thirds. So a sub 4 is 2 thirds. And we only have one more to go because we're looking for 5 terms, right? So a sub 5, or actually a sub 4 is the 5th term. Well, let's do a sub 5 for the fun of it. 2 to the 5th power over 5 times 4 times 3 times 2 times 1. Okay, 2 to the 5th, that's 32. 5 times 4 is 20, times 3 is 60, times 2 is 120. We call that 8, then this is going to be 4 up there, and this is going to be 15. So 4/15 is a sub 5. All right, so I think we did more than 5. We're probably good there. Let's just go ahead and highlight them. So there's a sub 1, here's a sub 0, so there's 2, there's 3, there's 4, and there's 5, and we did 6, so we overdid it. Okay, oh, and then it says plot the points, so let's just go ahead and plot the points. So let's just go ahead and do that. Let's say when n is equal to 0, we know that a sub 0 is 1. When n is equal to 1, that a sub 0, a sub 1 is 2. And when n is equal to 2, then a sub 2 is 2. When when n is 3, then a sub 3 is 4 thirds. Well, that's 1 and 1/3. Okay. And then when n is 4, Now we're at 2/3. Now we're less than 1, I mean. And we get even further down because a sub 5 is less than 1/3 because it's 4/15. So interesting graphing for just finding the plots that go with those terms of this sequence.